back to the session, right. So, in current session again we will discuss about the root locus. So, in the previous session we discussed about the introduction to the root locus, and then we were observing the construction rules of the root locus, right. So, today we would like to see the other construction rules of root locus, then one example of root locus and concept of angle of departure or arrival whenever we will completed the example of root locus. Okay. So, here in the construction of root locus, in the last session we discussed that this is my GS transfer function, and we were observing this as the pole of closed loop pole, because when we write the closed loop pole transfer function, so you can say it is given as CLTF is given as, you can say, GS over 1 plus GSHS, right. So, 1 plus GSHS basically act as poles of closed loop system. So, that is why whatever we are writing here 1 plus GSHS, that is 1 plus this term, what is DS plus KNS, basically it belongs to the closed loop poles of the system, and we are saying this is a basically a quadratic equation. So, last time we had seen the starting point whenever my k is equal to 0, in that case my ds was coming to 0. Okay. So, in that case we can say the closed loop pole is equal to the open loop pole whenever my k is equal to 0. So, when you put here k equal to 0, only ds term will remain here. So, ds term basically it is coming here. Okay. So, you can see in this equation only ds term will be remaining and remaining term would be 0, and this ds is very similar to the ds of open loop. Then we can say here the closed loop pole is equal to the open loop poles, right. So, here this is the condition whenever my k is equal to 0, and when I put k equal to infinity, so what I am getting k n s equal to 0. So, this term basically present in the denominator of closed loop transfer function, right. So, 1 plus GSHS basically it is what ds plus k n s. So, whenever my k is infinity, this term will neglect, only k n s term will become, and when I put k n s term is equal to 0. So, n s is basically what, it is the numerator of open loop system, right. So, whenever my k is equal to infinity, then my closed loop pole is equal to the open loop 0, because n s will give us 0 in open loop and ds will give us poles in open loop. So, here whenever my k is infinity, then this closed loop pole is equal to the open loop 0. So, this concept we had seen in the last session, that is our root locus will start from open loop pole and terminate at open loop 0. So, this is the importance of open loop. So, that is why in the every problem of root locus open loop transfer function would be given, and then we would like to observe and calculate the stability of closed loop system, right. So, now we will see here the basic rule. We need to find rule number 1, reason lie on the root locus. So, here I need to plot all the poles and 0 present in the open loop transfer function in the S plane. This is the imaginary axis and this is the real axis. Okay. So, in this plane we need to plot this poles and 0. Okay. So, here I need to look on certain point. So, I had drawn the location 1, location 2, location 3 and location 4. So, if I am standing at location 1, so I have to see in my right direction, is there any pole or 0, right. So, here number of pole and 0 is 0, nothing is here. Then I will move to the location number 2. Is there any pole on my right side? Yes, one pole is present on my right side. It means if I standing here at location 2, I have to look towards my right side. So, on the right side I am getting the single pole. It means my count is here odd, right. It means this region will lie in the root locus. Okay. It means which region? The region between two pole, the green region, you can see this shaded region will lie on the root locus. Now, I will stand on the location 3. Now, I have to look on my right direction. So, how many poles or zeros are here? So, if I count on the real axis, only 2 poles are here. Now, my count is here even. It means this portion, the area between, you can say, between the 2 pole will not lie on the root locus. Okay. So, this portion will not lie on the root locus. Now, I have to stand on the location number 4. Okay. Now, I have to observe how many poles and 0 lying on my right side. So, now only poles are available 1, 2, 3, it means count is odd. It means from this pole to the next pole, you can say if it is not given, assume to minus infinity, this whole area will be part of root locus. Okay. So, this is the way. First rule, you need to determine which part of root locus will be available on S plane. Okay. So, this rule is can be understood by this method also. So, if you want to know the why logically we are doing it. So, here this location point L 1, point L 2, L 3 and L 4, they should satisfy the angle condition. If they are satisfying the angle condition, then these locations will lie on the root locus. So, first I will go for L 1. So, I have to observe that if I am standing at L 1, so it will make 0 degree angle with you can say this pole, 0 degree angle with this pole, 0 degree angle with this pole, right. So, for angle condition, what is the condition? That the angle contribution of the point should be odd multiple of 180, right. Agar if it is coming 360, even multiple of 180, then it will not lie on the root locus. So, right now angle is 0, sometime it may be 360, then we can say this is not, this point is not part of root locus. Now, come to the location 2. So, whenever I am coming to the location 2, then I have to observe the angle contribution from the first pole to this point, angle contribution from next pole to this point, angle contribution from third pole to this point. So, here I will find that L 2 makes minus 180 degree with the first pole, you can say it is S 1, and remaining pole you can say here this is S 2 and this is S 3. So, with S 2 and S 3 it is making 0 degree, right. So, that is why this is the odd multiple of 180. So, this region will lie on the root locus, the region between the 2 pole. So, whenever I am standing here this location, I would like to know what is the angle contribution from origin, angle contribution from this pole and angle contribution from this pole. So, if I am here, the 180 degree from S 2, 180 degree from S 1, total is 360 degree. Again it is even multiple of 180, it means this region will not lie on the root locus, because angle condition says it should be odd multiple of 180. So, that is why location L 3 will not lie on the root locus. The same way when we see the L 3, again L 3 will be the odd multiple of, you can say if I am standing here L 4, I need to see angle contribution from S 3, S 2 and S 1, and it will come odd multiple of 180. So, all the region will lie on the root locus. So, this is the alternate method. You can go for this logic, or you can calculate angle with each and every pole, then you can determine which region lying on the root locus. Okay. Now, rule number 2, we need to determine how many branches present in the root locus. Basically, these branches will tells you the movement of pole towards the infinity, right. Because we are doing what? We are varying from k equal to 0 to k equal to infinity, and in the previous slide we had observed that k equal to infinity location is open loop 0. So, basically our open loop poles will vary from k equal to 0 to infinity and terminate at open loop 0. It means it will follow certain path, that path will be the branch of root locus. Okay. So, how many branch will root locus have? We need to calculate from this method. Okay. That is, we need to calculate the open loop poles and we need to calculate the open loop 0. Okay. So, here case 1, if open loop poles are greater than number of, you can say open loop 0, then number of branch will be equal to number of poles. Okay. So, if this condition is satisfying in the transfer function, if poles are greater than 0, open loop poles, then number of branch will be equal to number of poles. When we solve the numerical, then this concept would be clear to you. Then second case, if the number of open loop zeros are greater than open loop poles. Okay. For example, you can take s plus 3 divide by s plus 2. So, here number of you can say open loop zeros are greater than the zeros of the number of open loop poles G s equal to given by this. Okay. So, here you can say the number of branch in the root locus will be equal to the number of zeros. So, this type of transfer function is improper transfer function, because the power of numerator is higher than the power of denominator, right. So, whenever we have to design a system, then we have to consider the proper transfer function. In that case, the power of numerator should be less than power of denominator. And whenever we are discussing about the critical transfer function, in that case the power of numerator is equal to the power of denominator, right. So, here if we want to know how many branches will be available in the root locus which is terminating to infinity, which is approaching to the open loop 0, then I have to write this formula n equal to p minus z, where p is the number of open loop pole and z is the number of open loop 0. So, this will tell us the number of branches will terminate to infinity or they will approach to the open loop 0 in root locus. Okay. Now, come for the rule number 3, that is the angle of asymptote. So, angle of asymptote will tells you whenever your branches terminating to infinity in the root locus, what is the direction, in which direction they should follow to reach to the value of infinity or to achieve the location of open loop zeros. Okay. So, here we need to determine angle of asymptote, that is phi, from this formula 2 q plus 1 180 over p minus z, right. This is the basic formula, analyzed formula. So, here this q value will depends on p minus z. Okay. So, p minus z will tells you what should be the value of q. If I am saying p minus z is equal to 1, so q value will have single value, that is 0. If I am saying p minus z is 2, it means q will have 2 value, that is 0 and 1. If I am saying p minus z is equal to 3, then q will have 3 value, that is 0, 1 and 2. So, depending on the value of p minus z, q will be determined and that will give us the angle of asymptote. So, whenever I put n, that is where you can say n equal to p minus z, whenever n is equal to 1, phi is 180, q equal to 0, it will have single value. So, you can say q depends on p minus z. So, whenever p minus z is equal to 2, that is n equal to 2, then phi will have 2 values, that is 90 and 270, you can put values here. So, it will have 2 values of q, 0 and 1. Whenever p minus z n is equal to 3, so q will have 3 value 0, 1, 2, corresponding to that phi is 60, 180, 300. So, this is fixed for every example, right. So, whenever you have to observe n is 1, so you have to directly write phi is equal to 180, you can calculate. If n is 2, and you have to write directly 90 and 270, there would be 2 angle of asymptote. If n is 3, then you can write 60, 180 and 300, they are the angle of asymptotes. Okay. So, here if n is equal to 2, it means 2 roots of root locus are terminating at infinity and requires 2 angle of asymptote, which shows path to the root locus branch to terminate at infinity. If n is equal to 1, it means only one branch of root locus will terminate at infinity and angle of asymptote required would be 1, and it will tells the path in which direction it should approach to the infinity. So, this is the meaning or importance of angle of asymptote. Now, we will come for the rule number 4, that is calculation of centroid. So, centroid will tells you the intersection point on the asymptote of the real axis. So, whenever you are drawing the angle, so at which point you should draw on the root locus or which point on the real axis that you have to follow on the root locus, it will be given by the centroid point. Centroid point is given as c equal to summation p minus summation z over p minus z, where summation p is the real part of sum of poles, summation z is the real part of sum of 0. It means whenever complex poles and zeros are given, you have to consider only the real part, you do not have to consider the imaginary part in calculation. Okay. And this will gives you c. So, basically whenever we need to draw c, this is my C, and from this C I need to draw the angle of asymptote, right. These angles are coming, you can say one angle is here, this is the angle 1 phi 1, this is my phi 2, and you can say this is the phi 3 and this is the phi 4. It means 4 angles coming here, right. Now, come for the next step, step number 5, calculation of breakaway point. Okay. So, what is the breakaway point? Whenever our two poles are overlapping. Okay. So, you can say whenever if we take the previous example of the root locus, whenever we were assuming that our quadratic equation was s square plus 2s plus k, and when we put here k equal to 1, then we will get here our repetition of root on the real axis, that is at -1. So, whenever our pole will overlap, after which what will happen, this pole will leave the real axis, okay, and they will try to terminate at infinity. So, the value, or you can say the value of k at which the poles are leaving the real axis, because when I further increase the value of k from 1 to 1.5, they will come in imaginary axis, they will come in imaginary axis. It means they are leaving the real axis when I increase the value of k. Okay. So, that is why the point, whenever my root locus leaves the real axis and going in the imaginary axis, that point is known as a breakaway point. So, basically whenever the two poles overlapping on the real axis, so we can say that would be the point of breakaway point. Okay. So, you can say the maximum value of k at which the root locus moves away from its path, the value of k at which root locus leaves the real axis, that point would be known as breakaway point. Okay. And how we can determine the breakaway point? We need to use the quadratic equation 1 plus GSHS equal to 0, okay. And then we need to find k, we have to equate the equation in terms of k in RHS and remaining term on the, you can say LHS, and then we need to determine dk by ds equal to 0. Then whatever roots are coming from this equation, that will give us the breakaway point. Okay. So, the root locus can be related to basically you can say to the overdamped system, settling point, whatever term that we were discussing in the unit 2, we can relate it to the root locus also, because Routh-Hurwitz criteria unable to explain the relation between the overdamped, undamped system and settling point concept whenever we were studying the root locus. So, here with Routh-Hurwitz criteria. So, with the help of root locus, we can revive this concept. Okay. So, here you can see if I am having a root locus like this, suppose the concept of that term s square plus 2s plus k, if you remember from the previous lecture, this was the quadratic equation. I was varying the value of k from, you can say 0 to infinity. So, I was varying the value of k from 0 to 2. So, what is happening? My pole is keep shifting. So, at -1 what will happen? This pole will keep shift towards here and overlapping of poles will takes place. One pole will move up direction to the value of +1, this is 1 j, and second pole will move to direction of -j. It means this is the direction, it will move like this. So, what is happening here? So, whenever my k is greater than 0, so here at open loop pole, what is the value? K is equal to 0. Here at origin k is equal to 0, because this is the location of open loop pole, right. So, now what I am doing? I am increasing the value of k from 0 to 0.5. Now, my pole is shifting. At -1 what is happening? You can say at k equal to 1, these poles are overlapping. So, if you relate to the time domain analysis, the repetition root will tells you a critical system or critically damped system, right. And whenever my k is greater than 0, but it is less than 1, then we can say my roots were real, but different or distinct. So, it will be the condition of overdamped system. Whenever my value of k is greater than 1, it will leave the real axis and it will try to move in the imaginary axis. It means my roots are real and imaginary and it will be a underdamped system. Okay. and further when I move the value of k, if it touches the imaginary axis at certain point, then we can say the system would be marginally stable. Okay. So, this condition will come when we change the value of k. Okay. So, here one more numerical we can consider here. Consider transfer function given like this. The root locus plot of the system passes through s equal to 0. Okay. So, here it is given our root locus of the system is passing through a pole value or a root value s equal to 0, and we need to determine the value of k at this point. So, again to determine the value of k, we need to follow here magnitude condition, right. So, what I will do, I will calculate the mod of this mod of g s, I will apply the magnitude condition. So, k over s cube plus 4 s square plus s minus 6, I will calculate it mod for value of s equal to 0 and I will put it equal to 1. So, here if I put s equal to 0, so this will become k over minus 6 should be equal to 1, or if I further solve it, so k is coming here equal to 6. So, value of k is equal to 6. So, here C is the correct option, right. So, whenever s is equal to 0 given in the equation, it means it is satisfying the root locus. So, that is why I am putting s equal to 0 for the mod of g s, and if you do this, then you will get the value of k. Okay. This is the solution of it. Okay. So, now we will see one more numerical. So, in this numerical we will see a unity feedback system has open loop poles at s equal to minus 2 plus minus 2 j, s equal to minus 1 and s equal to 0, right, and one more 0 is available at s equal to minus 3. So, what is the asking? It is asking that the angles made by the root locus asymptote with the real axis. So, first we would like to plot these poles and 0 on the s plane, then we can calculate this thing. So, here I will plot my real value on the x axis, imaginary on the, you can say, imaginary axis. So, here one pole is at minus 2 plus 2 j. So, suppose this is minus 2 and this is the location of plus 2 j. Suppose this is the plus 2 j is here and this point is here. This is the one pole. Second pole is available at minus 2 j. Suppose this is the point of minus 2 j. Okay. So, these two poles are here. Next pole is here at s equal to minus 1. So, at minus 1 I am assuming this is the location of my one pole. Now, next pole is here at s equal to 0, one pole is at the origin, right. So, in this way we have drawn all the poles. Okay. Now, one 0 is available at s equal to minus 3. So, this point is minus 3 and I am assuming here one 0 is available here. Okay. So, now what we need to calculate, we have to calculate here the angle of asymptote. So, here the angle of asymptote phi is given as 2q plus 1 multiplied by 180 divided by p minus z. Okay. So, I told you in the previous slide the value of q will depends on value of p minus z. So, I need to calculate the p minus z. So, I need to count how many poles are here. So, you can say this is the pole 1, this is the pole 2, pole 3 and pole 4. So, 4 poles are available. So, value of p is here 4. Now, whenever we would like to calculate the number of 0 present in the system. So, only single 0 present here at minus 3. So, we can say 0 count is here 1. Now, if we calculate p minus z, it is coming here 3, right. So, what would be value of q in this formula? So, q will have here 3 value, that is 0, 1 and 2. Okay. So, now for this value of q, I need to determine what should be value of phi. So, whenever it is having the 3 value, then I told you it will have the 3 values you can calculate. So, whenever you put here q equal to 0, this will become 180 over p minus z is 3, this will become 60. This is your phi 1. Now, phi 2 for q value equal to 1, this is become here 3 multiplied by 180 divided by 3, this will gives you 180. In the same way, when you calculate phi 3 for value of q is equal to 2, this will become 5 it will become 5 by 3 180, and if you solve it you will get around 300 degree. Okay. So, these 3 angles are coming from this given example. So, now we need to see the option. So, we need to see option A, 60 is here and 60 is here, 60 is here, 60 is here. So, again we can't eliminate the option. Now, we can come for second answer phi 2 equal to 180. So, 180 available in option A and 180 is available in option D. So, we can eliminate here option B and C. Now, my third angle is 300. So, now you can see the remaining angle is minus 60 here and remaining angle is 30. So, which one is the correct answer? So, in this case just we would like to see the representation of angle basically. So, I told you in the previous slide. So, when we move in clockwise direction, okay, you can say suppose this is my S plane. Okay. So, if I am moving here in anti-clockwise, then my phase is here positive. Whenever I am moving in the clockwise direction, then my phase would be negative. So, if I have to plot the 300 degree, so this is my 0 degree, this is the 90, this is 180, this is 270 and 300 will come around here. So, I will move in anti-clockwise 90, 180, 270 and then further to move 300 I will add 360. So, this angle is here 300 degree. So, if I move in clockwise direction, so I can write this movement is around minus 60. Okay. So, here 300 degree is equivalent to minus 60. So, in this numerical this 300 is equivalent to minus 60. So, option A is correct, right. So, this is the way that we can calculate the angle of asymptote in the root locus. So, the remaining concept what will happen when number of pole is equal to 0 in the root locus we will discuss in the next lecture. Okay. So, thank you for today.